Hi, I'm Josh, and I'm a biochemistry PhD student. I first got into science after I was diagnosed with celiac disease in high school, because I felt firsthand how powerful biology can be when it's working against us. Now, I'm flipping that story by engineering cells that can work for us.
We can imagine cells as being like an orchestra. Here, the performance consists of different songs, and these songs are all played by a standard set of instruments. Similarly, cells contain thousands of different proteins that each help the cell in a unique way. These proteins all consist of 20 standard amino acids that act as the molecular instruments of the cell. But imagine that the orchestra has a rare, new instrument that could transform music. The catch is that no one knows how to play it, it's expensive to maintain, and you'd have to rearrange the whole orchestra just to fit it in. Similarly, cells have a special 21st amino acid called selenocysteine, and when it's put into proteins, making selenoproteins, it transforms their chemical properties so that they can catalyze reactions that normal proteins can't. And because of these abilities, many selenoproteins play important roles in mitigating conditions like cancer metastasis and neurodegeneration. Also, engineered selenoproteins have wide-ranging applications in producing clean energy, helping crops tolerate climate change, and designing more stable drugs.
The problem is that cells are really constrained in how they can actually use selenocysteine, restricting both the types and amounts of selenoproteins that can even be produced, meaning that most of these applications just go completely unrealized.
So, my research goal is to create engineered cells that can make high quantities of all kinds of selenoproteins, allowing researchers everywhere to explore their applications. To do this, I'm redesigning the cellular pathways that insert selenocysteine into proteins, and to test new molecular designs, I use cells that glow green according to how many selenoproteins they make. In this way, we can easily pick out the best performers on a plate full of different designs by just looking for the brightest green signal. And after finding promising designs, I then study them to understand why they worked with biophysics. Essentially, we look at how the design changes small forces, structures, and timing in the pathway to help us make the next round of designs even better. And using these methods, I recently redesigned a selenocysteine carrier, also known as a transfer RNA, to hold on to selenocysteine more tightly, and that increased selenoprotein production by 400%.
One thing I love about this kind of research is that its impact extends well beyond academic circles.
And that impact starts with access. So, I designed and brought synthetic biology experiments to classrooms across Clark and Jackson counties, from third graders to high school seniors. And to create long-term impact, I helped develop a research internship program in our lab for local students, and I turned my lesson plans into a series of synthetic biology courses for secondary school students.
With my work, I'm not just composing the next great song. Instead, I'm tuning the orchestra itself so that musicians everywhere can create their own masterpieces in therapeutic design, renewable energy, or biomedical research. And of course, thank you to the ARCS Foundation for considering my application.